water, earth, fire, air. Long ago, the four nations lived together in harmony. Then, everything changed when the Fire Nation attacked. Only the Avatar, master of all four elements, could stop them. When the world needed him most, he vanished. 100 years passed, and my brother and I discovered the new Avatar, an airbender named Aang. And although his airbending skills are great, he has a lot to learn before he's ready to save anyone. But I believe Aang can save the world.
Yeah, so long ago, Socrates re referenced the Platonic solids, the five Platonic solids, in the writing of Timaeus, and he assigned each element of the five basic elements to a Platonic solid. So the icosahedron is water, the cube is earth, the tetrahedron was fire, the octahedron was air, and the dodecahedron was ether or ether. And so that's the first explicit historical reference that we have for the Platonic solids. And then later on, the Platonic solids got connected to things like sacred geometry. There's a lot of philosophical, metaphysical, historical connections to the Platonic solids and geometry. And for that reason, a lot of mathematicians have been historically fascinated by the Platonic solids and their properties. Here. So these Platonic solids are also called regular polyhedra. They kind of look like this. And this is an example of the, if you remember correctly, this is the octahedron, spelled like such. So that's the octahedron as an example. Here we have a face. That's a triangle face. Here we have an edge. And right here we have a vertex. So what is a regular polyhedron, which is the singular for polyhedra? So a regular polyhedron is a closed solid figure whose faces are regular polygons. So regular polygon meaning, you know, an equilateral triangle or a perfect square, things like that. And a regular polygon is what we just described actually. So it's a 2D planar figure, 3 or more sides of equal length and interior angles of equal measure. So triangle, square, pentagon. I can't draw pentagons, but pentagon. And we'll see what actual pentagons look like. Hexagons. Let me see if I can draw that really bad hexagon, but shapes like that, octagons, and so on. So what polygons will we use to create a polyhedra or polyhedron? Yeah, polyhedron. So we can use the regular triangle. We can use, well, this is more like a rectangle, but here this isn't, we could call it a square. If we draw a more perfect rectangle, that'll be a perfect square. And we can also use pentagons. We can use pentagon. See if it, nope. That's a hexagon. But yeah, we can use different shapes for different polyhedra. So here's an example, the very classic example that I know everybody ended up drawing something like this as children. or maybe you are a child still in your hearts. But let's start with a square. Duplicate, we can duplicate this square so that both are congruent. So these are two of the exact same square. And if you don't believe me, I can't draw squares, so I actually did copy and paste this. These are congruent squares. And then we're going to overlay them like so. So there's the one square, there's the other square. And then we're going to connect the vertices like so to make the other edges. And notice we have a square over here, control squares, and we have a square over here, a square up top, and a square on the bottom. So that would be a polyhedra. And Platonic solids are a specific type of polyhedra. So what are Platonic solids on that note? So a Platonic solid is first off convex, which we'll cover in just a second. It's a regular polyhedron, which we just discussed the definition for regular polyhedron, in 3D Euclidean space, which is just fancy for really nice, distinct grid space that we can do. Nothing super curvy or spherical, hyperbola, just regular 3D grid space. And then we need congruent faces of regular polygons. So, like we just said earlier, we need to have either a perfect square or an equilateral triangle or an equilateral pentagon, equilateral hexagon, whatever we're using. Those things need to be congruent both in length for each side and for each internal angle. All need to be congruent. And lastly, the same number of faces must meet at each vertex. That is a very important part. Okay, so let's do a little bit of an example to show you like what's the simplest case. So we're going to start with an equilateral triangle. For an equilateral triangle, the sum of the internal angles must be 180 degrees. And so if we divide that by 3, we get 60 degrees per internal angles. And that's exactly what we have over here. Now we're going to duplicate it twice over from the original. So now we have 3 triangles. And then we're going to arrange them like so that there's like a 180-degree gap between these 2 triangles. And notice that there's 3 triangles meeting at the same vertex. And we can actually calculate the angle of this gap by adding up all the internal angles. This angle is going to be the same as this angle. Or you could rephrase it as a complete turn is going to be 360. So 360 minus 60 minus 60 minus 60 is 180. Now that we've noticed these sides, we're going to glue together the sides across the gap. Like so. So we're going to glue together this side and this side. And then that's going to turn into this weird looking 3D shape. Now I have this example right here. Let me just go ahead and unfold it. So here is our figure, right? It's exactly the same as our drawn figure. We're going to see these 2 bottom pieces. Here's our tape. We're going to glue them, or in this case, tape them together. And notice that's what we call a tetrahedron. And there's no base, right? At least the way we've done it, there's no base. But to make it a point that at least in a virtual space, there would be a base, we could take the base on. And we know that this shape right here if we traced it out on a piece of paper, would be a triangle that is exactly the same as the other faces. And so this shape is called a tetrahedron. It's the easiest Platonic solid to make. And then let's go to the next Platonic solid. So what other Platonic solids can be built with n equals 3 sides? So since the 2D construct we built the tetrahedron from was already congruent, let's add another equilateral triangle. Just to see how many triangles we can do. So if we do that, we're going to have 1, 2, 3, 4 equilateral triangles meeting at the same vertex. Now the gap has decreased from 180. Since we added another triangle, this is going to be another 60 degrees. So 180 minus 60 is going to be equal to 120. And that's exactly what we have here. So now we're going to notice that there's a 120-degree gap between this side and this side. We're going to glue those sides together. And we're going to end up with this shape right here. But that's not a Platonic solid. No, yeah, because this is clearly not a triangle base like we had last time with the tetrahedron. So this is what's called a pyramid. Some people call this a pyramid. Rectangular pyramid, rectangular prism, whatever you want to call it. But whatever it is, not a Platonic solid. But if we duplicated this shape, right, and then we glued the bottoms together, right? So we have a regular pyramid like so, and then we're going to duplicate it, and we're going to glue the bottoms together. We're going to end up, this is going to look a little weird because I'm not a very artsy craftsy person, but we're going to end up with a tetrahedron. Or sorry, not a tetrahedron, an octahedron. And it's called octa because it has 1, 2, 3, 4, 1, 2, 3, 4, and then another 1, 2, 3, 4. So that's 8 faces, octahedron. And that's exactly the first example we used in the first page. And that is a Platonic solid because all the outer faces are triangles that are congruent. And if you count the number of faces that meet at a vertex, that's 1, 2, 3, 4 faces, just like that. This is called an octahedron. So it's the second Platonic solid. Let's move on to the next one. Okay, but seriously though, what other Platonic solids that can be built with this weird triangle trick that we happen to like? Oh, the screen share is lagging, so I'll let it catch up. Yeah, what other Platonic solids can be built with n equals 3 sides, with basic shape n equals 3 sides? Okay, so now let's do another triangle. So that's 1, 2, 3, 4, 5 triangles meeting at the same vertex. And so now that's, we subtracted another 60 degrees by adding another triangle. So then this gap right here is going to be also 60 degrees. Okay, well, if we try the same process, right? Glue the sides together, notice the gap, glue the sides together. Okay, well, then we get this weird shape that I haven't constructed physically, and we'll see why. So it's like a weird pentagon base pyramid, right? Okay, well, it's not Platonic yet. Okay, not a Platonic solid. Let's duplicate it because that's what we did last time. Surely it could work. duplicate the shape, glue the bottoms together again. Oh, okay, but this is a weird uh, drawing, but it gets the point across. Here we have, if we look at the top, we have 1, 2, 3, 4, and 5 triangles all meeting at the very top, right there, kind of like a Christmas tree. They all meet at this vertex right here, so that's 5 triangles. But if we count, say, another vertex, say over here or over here, when we only have 1, 2, let's see, and then the bottom we have 3 and 4 triangles that meet at this vertex way in the back. So this contradicts the Platonic solid definition, which we said that was the last statement of the Platonic solid definition. If we look back over here, the same number of faces must meet at each vertex. So every vertex has to have the same number of faces meet. Okay, let's move on. So this attempt failed, right? Bad, not a Platonic solid. Okay, let's try something else. Let's try to make like a net. We're going to base it off of the original attempt that we had because that worked. And then let's try and add another triangle to this. Okay, so we make this shape. And let's duplicate this shape so it looks like this. It's going to be, I think, 5 duplicates should be enough. And notice this shape is created from this construction. Notice this shape is created. So those are the last 2 constructs, or some of the last few constructs that we used. This shape is also constructed. And so if you look at the vertices, there's, let's see, 1, 2, 3, 4, 5 triangles meeting at this vertex. At this vertex is 1, 2, 3, 4, 5. Let's see. Well, we won't see it yet for this vertex or this vertex, but when we fold it, there's going to be the other 2 triangles that meet at that vertex. So now we're going to glue the green sides together and the blue sides together after gluing together the green sides. And what we're going to get is called the icosahedron. So notice this shape right here. That shape look familiar, right? So this is the physical construction. Again, not an artsy craftsy person. So if it looks weird, that's just because I suck at arts and crafts. That's not because it's not a platonic solid. This is a platonic solid, I promise. And that's the physical construction. It's okay. We tried 5 triangles, right? Let me just 1, 2, 3, 4, 5. Wait, hold on. Sorry, this shape is messing with my head. But we've tried 5 triangles, right? 1, 2, 3, 4, 5 triangles meeting at the same vertex. Why not try 1, 2, 3, 4, 5, 6 triangles meeting at the same vertex? Well, we immediately notice that there's no longer a gap to glue sides together over, right? That gap is officially closed because we added the last triangle. The last 60 degrees has been taken up by the 6th triangle. So there's no gap to glue sides together over, right? And so this is actually a complete shape. If right, yeah. So right, if I picked up this hexagon, is what we just made, it's a hexagon. We picked it up and tried to fold it into some kind of pyramid shape like we did last time. You can't. Can't do it. So the internal angle measure is going to be 60 degrees times 6 triangles, which gives us 360. That's a complete shape that we can't fold to make a concave or convex uh, polyhedron. Which, by the way, a convex, I said I was going to cover that. Convex simply means that if I drew a line, if I treated this as like a set of points, and I drew a line through this shape, right? If I had a piece of string and I tied the string from one end to the other end, going through the shape, then the entire string should be inside the shape. That's what convex means. If it were something like concave, right, something like this guy, where it's like bent up, then the string, if I tied a string through here, it's not going to be contained by this set, right? It's not going to be inside this flat plane. Whereas the string would be entirely contained in a shape like this. So if we insisted though, and we really tried to make it 3D, it might look like this. And so we've transformed things. It's not quite right. And also if we counted the triangles, right, we have here we have 1, 2, 3, 4, 5, 6 triangles meeting up here. 1, 2, 3, 4, 5, 6, right? And then if we counted any of the back vertexes or the front vertices, we have, what is this? We'd have 1, 2. And then if we had a duplicate pyramid moving back down here, we'd have 1, 2 triangles meeting here. So that'd be 1, 2, 3, 4. So we'd have 4 triangles meeting at this vertex and 6 triangles meeting at that vertex. So it's definitely not Platonic solid. So unfortunately, there's no other Platonic solids to be built with n equals 3-sided congruent elementary shapes like triangles. Okay, so I said there are 5 Platonic solids. Let's discuss the other 2. So now we're going to try building Platonic solids with n equals 4 elementary shapes, 4-sided elementary shapes. So squares. So we're going to start with a square. Boom. We're going to duplicate it. Boom. Well, immediately we notice we can even do this with pentagons. Right? If I have a pentagon, I duplicated them. I can't make any kind of closed shape with this. Same thing with 2 squares. Now we're going to try with 3 squares meeting at the same vertex. Notice that since it's a perfect square, the internal angle measurement is going to be 90 degrees. So that leftover gap is also going to be 90 degrees. And we can see that because also if this is 360 rotation, right, that's 360 minus 90 minus 90 minus 90, which gives us a leftover 90. Okay, well, now let's do the same thing that we did before with the triangles. We're going to glue this side and this side together. And this is going to look like some weird half-shaped cube. And then we're going to take this guy and we're going to duplicate him. So I made him look like this guy, so that way they're different. And then we're going to glue them together. Glue these sides together. And so now we end up with our cube. So this is also called a hexahedron because it has 6 faces right there. 6 faces. It's also called a cube. No one's going to correct you or be super technical unless they want to be, but it's called a cube. Okay, well, hypothetically, let's say if we try to make more platonic solids out of this, well, we would have to do it with, well, we definitely can't do it with four squares, right? Because that would make a complete shape, and we ran into that problem earlier. So and we definitely can't do it with 2 squares because we discussed the problem that we can't make a closed shape. Okay, so let's try with 3 squares again. See if we can construct something similar. If we duplicate, oh, okay, never mind. Correcting my past self here. There's 4 squares. If we duplicate this construct, we're actually going to end up with another cube, which this is actually congruent to this guy. Crazy. So we can't draw any more unique platonic solids with 4 sides. But also, for the same reason, we can't pick up a hexagon. We can't fold a hexagon into a particular shape because it's already a complete shape. Same reason we can't fold a perfect square made up of other perfect squares into a new closed polygon shape. Here's our constructed cube. And if I unfold it, by the way, just unfold it. So you guys can see the inside. Right, so right there, I don't know if you guys can see it. There's the inner side for this side. And then right over here is that other duplicate part. But even if you don't really see it, this is still very clearly a cube that is very clearly a platonic solid. Okay, well, unfortunately, there's no more platonic solids for n equals 4 or 4-sided elementary shapes. Okay, now let's try with pentagons. So let's start with a pentagon. The first thing we notice, or well, the first thing you can look up, because I looked it up, is that the internal measurement for a equilateral pentagon is 108 degrees. That means that total is going to be more than 360 degrees. I think it's actually, let me see, 108 times 5, that's 0, carry 4, 90, so 5, no, it's 540 degrees. Yeah, so that's the total, in case you wanted to know. So let's start with the pentagon. We're going to make this arrangement. And the basic arrangement that we're going to start with here, if you don't notice it, it's going to be like this. Actually, let me change my, yeah, it's going to be like this. That's going to be your basic arrangement, and that's going to occur the entire way through. So we made this arrangement. We're going to duplicate it. Okay. So we have pentagons that have been glued together like on these sides. And then we duplicate this arrangement and then glue this side, these sides together. So now we're going to notice this gap here. We're going to glue these sides over this gap. And we're going to do that for every single other side of both constructs. And then when we put it together, should have something that looks like this. This is called a dodecahedron. And in case you were wondering, the gap angle is 360 minus 108 times 3, which is 36. That's for 5 gaps, that's a total of 180 degrees, which is the total angle deficit, is what it's called. Okay, so we've shown for triangles that there's no more Platonic solids we can build. We've shown for squares that there's no more Platonic solids that we can build. Let's try with pentagons. I can find my shapes. Right. So let's try with pentagons. So I have this familiar shape that I pointed out earlier for the dodecahedron construction, which, by the way, looks like this. Again, I'm not an artsy craftsy person, but it's very clearly a Platonic solid. And so let's take another pentagon. And what we're going to do is, this is 1, 2, 3 pentagons, right? That meet at this vertex right there. So now let's try with 1, 2, 3, 4 pentagons. And when we try this, it doesn't work. This little gap here is too small for this pentagon to fit. And so there's no more pentagons that we can fit at one vertex because we just don't have enough space. And so there's no more Platonic solids that we can build with pentagons. Okay, so I said in the beginning, there are 5 Platonic solids. Can we build more, right? We've started with triangles, we started with squares, pentagons. Why not try a hexagon? Trying to build Platonic solids out of a hexagon. Well, let's try it. We start with a hexagon. All right, started with a hexagon. If you look it up, the internal angle measurement is 120 degrees for a equilateral hexagon. And if we divide that up by 6 triangles, we get the same familiar hexagonal shape that we had that when we built out of 6 triangles. So that means that this angle right here is 60 degrees. And so we can derive the internal angle by saying that 60 degrees is the internal angle here is 2 of these triangles. So that's 60 degrees plus 60 degrees, which is 120 degrees. Or you could just look it up. Okay, so let's build a construct. Let's try 3 meeting at a vertex because we talked about if 2 polygons meet at a vertex, we can't make a closed shape. Let's try 3. So there's our construct. Notice there's no inner gap here. So there's nothing to fold across over here. But let's really try to insist and really try to make it work. Okay, well, let's try and glue these sides together across this gap, which we know actually is 360 minus 120 times 2, which is 1, 2, which equals 120. So this gap angle right here is actually 120 degrees. So if we glue these sides together, boom, 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 glue all those sides together, the hexagons will fold on themselves. So here's a physical example of that. We have our similar hexagonal 3 hexagon construct. And we have our gap deficit here. We're going to glue these sides together. Oh no, you can already see the hexagons are starting to morph. Okay, let's try another side. We're going to glue these sides together. Oh no. Yeah, we're morphing these hexagons. And we end up with this. I don't know what this is, but it's not a platonic solid, and we can't duplicate it to make more platonic solids. So it's pretty clear that in the Euclidean space, we can't make more platonic solids. So there are no platonic solids for n greater than 5 sides. And so there's just no more platonic solids, right? And you can't make a polygon out of n equals 2 sides, right? And you definitely can't do it with n equals 1 side. So there's really only 5 platonic solids. Okay. Now some of you might say that doesn't feel convincing, even though I've done the physical demonstrations. Maybe we can do some math for it. Might be a little bit hand wavy, but we can do some what's called it's like a combination between topology and combinatorics, right? This is a bit of a bonus proof. So let's remember our platonic solid definition, right? And this is going to be a key point here. So in topology, there's something called the Euler characteristic, and we calculate it by taking the number of vertices, subtracting the number of edges, and adding the number of faces. Now, for closed polyhedra, it's always going to be 2. And here's a table showing the Euler characteristic for all of our platonic solids that we showed earlier. They're all 2. But this is true for all convex regular polyhedra, is that the Euler characteristic is 2. Okay, so let's let P be the number of edges of each face, and Q be the number of edges at each vertex. So if I had, let's see if this works. Pentagon. No. Let's see. Let's try a square. We're going to copy it. We're going to paste it. Paste it again. Right. So this is our familiar construct that we use to make the hexahedron, or the cube. So it meets at that vertex. And so since there's 2 of these constructs, there's going to be 1, 2, 3 faces meeting at one vertex, and then the same for the other construct. Yeah, and if we built the construct, there would be the number of edges at each face. So for this face, it'd be 1, 2, 3, 4, right? And for the number of edges at each vertex, that's 1, 2, 3, 4, right? And so, but here's a weird thing, actually. Now that I think about it, this edge is being counted twice between these 2 squares, right? Same with this edge. And for each vertex, see, so there would technically be another vertex over here once we built the cube. This vertex is counting this edge for this vertex and this vertex over here. So technically we're counting this twice, right? So this is P times F is the number of face edge combos that we're counting. And same with QV, which is the edge vertex combos. So PF is doubly counted. So PF is, if we wanted to say that this is the total number of E, or edges, then it would be 2 times E, because we're double counting. And because of our definition, right, same number of faces meet at each vertex, that means that the number of edge vertex combos is equal to the number of face edge combos. Let me say that right here. But that also means that since this equals this and this equals this, that means that this equals this also. Okay, so here's the topological proof. And I'm going to kind of talk through it because it's a bonus proof. We've already proven what we need to prove. Let me write it below here. Okay, so we're going to use this fact, and we're going to use the Euler characteristic too, right? And we're gonna say that PF equals 2E. So then E equals PF over 2. All right. And if I do the same thing for QV, then QV would be, or E would be QV over 2. And so we plug that in here, here. We're sorry, we're actually solving for V and F. My bad. So this is PF, it equals 2E. We want to solve for F. So what do? We divide by P. So F is equal to 2E divided by P. And for QV, that's 2E. What do we do to solve for V? That's divided by Q, so 2E over Q. Just like that. And so we plug it in just like that. And so now everybody's in terms of E. Now we can multiply everybody. Let me draw it different. We can multiply everybody by 1/2. And we can also multiply everybody by 1 over E, so 1 over 2E. And we're going to cancel out 2E here, 2E here, 2E here. This E is going to be divided by 2. Or this is going to cancel out and be a 1 over 2. And then this 2 is going to cancel out. It's going to be 1 over E. And so you see that all right here. So then you have a 1 over Q, right? Because the 2E canceled out. You have a 1 over P because the 2E canceled out for that one. We're going to move this 1/2 that's over here. We're going to move that over here because it was negative. We're going to make it positive by moving it to the other side. And a weird thing to note, well, I guess it's not weird, it's just logical. But here's an equation, right? If we're adding a strictly positive number of edges, right? Or the reciprocal of the number of edges, because we can't have negative edges. We can't have 0 edges for a regular polyhedra. So this side, right, is strictly positive because E is strictly positive. And so if we're going to make this guy go away, we're going to make this right-hand side less than the left-hand side. In other words, we've made the left-hand side greater than the right-hand side. All right? This is the same as saying the right-hand side is less than the left-hand side. Okay. And so this is kind of like a trick. It's not that easy to see, but there's only 5 possibilities to build between these. And so we can actually test this out. So we know that the number of edges of each face has to be at least 3. Or sorry, at most 3. Um, no, at least 3. It has to be at least 3 because the base case we built was a triangle. But we can also demonstrate it with the cube as well. So if we take P or Q, doesn't really matter. Take P or Q, we make that 3. So that's 1 over Q plus 1 over 3 is greater than 1 over 2. And so 1 over Q, let's actually add a page to this. Yeah. So 1 over Q plus 1 over P is greater than 1 over 2. We're going to let P equal 3. So then that's 1 over Q plus 1 over 3 greater than 1 over 2. And so 1 over Q must be greater than 1/3 minus, or 1/2 minus 1/3 is 3/6 minus 2/6, which is 1/6. Right? 3/6, 1/3 is 2/6, so that's a 1/6. So then if we cross multiply here, we flip the sign. So then that's Q has to be less than 6. So in the case that P is 3, Q must be less than 6. And since Q must be at least 3, right? That puts Q between 6 and 3. So 3 less than Q less than 6. So the distinct numbers between 3 and 6 is obviously going to be 3, 4, and 5. So if you see where I'm going with this, that means between these, you can either do 3, 3, 3, 4, and 3, 5. So these cases are the tetrahedron, octahedron, and icosahedron. All right. And then if we distribute the 4, well, we can't have 4, 3, and we can't. So we have 4, 4. And if we do 4, 5, and let's think about it strictly in terms of our inequality here. So that's Q is 4, P is 5. Is that less than a half? That's 5. Let's see. That's 5/20ths plus 4/20ths. And so that's equal to 9/20ths, which is not greater than 10/20ths, which is a half. So this doesn't work. And so this is the cube right here. And then the last one we can do is 5, 3, which was 5 pentagons meeting it, or sorry, 3 pentagons meeting at one vertex. Right, so 3 pentagons, this being the sides, the amber edges. And so if we test that out, that's 1 over 5 plus 1 over 3. That's equal to 3/15 plus 5/15. That's 8/15. Okay. Half of 15 is 7.5. So this is greater than 1/2. All right. And that's the bonus proof. A little bit hand wavy. I don't think everyone would understand it the way I explained it. But I hope you like the explanation for the Platonic solids and why there's only, let's see, it's kind of this 1, 2, 3, 4, 5 Platonic solids. And that's all for today. Thank you for watching.